In this example, we're asked to solve a second order differential equation, and it is non-homogeneous. So again, thinking of other techniques, we could use the y and h non-homogeneous part and the y corresponding to solve this particular problem. We're going to solve it with Laplace just to show that the two methods are completely equivalent at this point. As part of the Laplace transform, we're also going to use these initial conditions. So our first step is to take the Laplace transform of the entire differential equation. So we're looking at our equation up here, and we just go term by term. The transform of y double prime will be s squared y of s minus decreasing s's, increasing derivatives of y. All of that is the Laplace transform of y double prime. Then we're going to subtract 2 of the transform of y prime. That's a little simpler. We have the sy of s minus the initial condition. All of that being the Laplace transform of the derivative of y. Then we have another 5 y's transformed. And last but not least, we have the transform of e to the negative t with a negative 8. And that will be 1 over s minus 1, or 1 over s plus 1. Now we gather the y of s terms. That's our unknown. We'll have y of s times, we have an s squared, we have a minus 2s, and we have a plus 5. Now notice there's a quick check we can do here. What were the coefficients of the original differential equation? 1 minus 2, 5. Oh look, 1 minus 2, 5. This is also the characteristic polynomial we would have had with our earlier methods, the ycy non-homogeneous parts. Looking at the rest of the equation, we also have minus s, so minus s times y naught, which is 2, minus the derivative, which is 12, and here being a bit careful, we have negative 2 times negative y naught, which is negative 2, and we already have the plus 5ys, that got put into this term here, and so we have this right-hand side unchanged. Last but not least, we'll start solving for the y of s, and that just means moving all these terms to the other side. So we'll have our negative 8 over s plus 1 plus 2s, and this altogether is minus 12 plus 4, that would be negative 8 on this side. It'll give us plus 8 on the far side. And our final product then is y of s equals negative 8 over s plus 1 s squared minus 2s plus 5, and the 2s plus 8 all over the s squared minus 2s plus 5. And again, by having this transformed version of y, we essentially have the solution, only in its transformed variable s. But if we want to go back to the time domain, we're going to need to use partial fractions to break this up into manageable pieces for the inverse transform. Copying out our solution again, let's take a look at the negative 8 over s plus 1 s squared minus 2s plus 5. That will equal an a over s plus 1. Unfortunately, this part here doesn't have any real roots. You can check for that. So what we're going to have to do is put a linear term on top and keep the denominator the same. And if we go to solve for the coefficients, we're going to have the cross multiplication giving us this combination. If we use the value s equals negative 1 as a sample value, we'll end up with negative 8 equals a times 1 plus 2 plus 5, or that's 8 in total, so we simply have a equals negative 1. If we look at the s squared coefficients, There are no s squareds on the left-hand side, and we're going to have an a s squared and a bs squared. And so b will be positive 1. And if we want to look for c, we could look at the constant coefficients. There's negative 8 on the left. There are 5 a's, and there are 1 c's. And that would give us c is equal to minus 8 minus 5 a's, which is minus 3. And that gives the decomposition of our first term here. The second term is actually fine. Let's see how this, first of all, looks when we put all the pieces together. We'll have negative 1 over s plus 1. That's our negative 1 here going into the form of the partial fraction decomposition. We'll also have s over s squared minus 2s plus 5. We also have c, which is negative 3 over s squared minus 2s plus 5. And we also have the original term at the end there. And we can gather some like terms. The first term, there's only one of those, but we do have an s plus a 2s. That gives us 3 s's over s squared minus 2s minus 5. And we have minus 3 plus 8. That'll be plus 5. 1 over s squared minus 2s plus 5. Having computed y of s now, our goal is to find the inverse transform of that y expression, that y of s expression. And we're close. One of these terms is fairly easy, it's in the table. These ones need a bit of work though, because they need some completing of the squares to get into their correct form. So let's take a look at that. If we have s squared minus 2s, to complete the square on that we need a plus 1. That would make this group of terms here a perfect square of s minus 1 all squared. But we just added 1. We can't just go ahead and do that because we want to. We'll have to subtract 1 as well to balance that. So we add those terms in, and we keep the original plus 5 there. And we'll do exactly the same thing on this other expression. We'll add 1 and group it with these terms. We'll subtract 1 and group it with the plus 5. Rewriting this one more time. I think we might need 2 more times before we're done, but we'll see. We have 3s over s minus 1 squared plus 5, 1 over s squared minus 1 squared plus 4, plus 4, when we combine those two outside terms. Now the challenge is we're using 2 entries for this one here. Let's call this term 2. For term 2, we're using the fact that the Laplace transform of s over s squared plus 2 squared is going to be cos of 2t. However, there's also this shifted term here of the s minus 1 squared. And for that, what we're using is the inverse of s minus a is e to the at, the inverse of f of s. Now the problem is, when we have this s minus a, it has to be every s in there. It has to be replaced by s minus some value. In this case, s minus 1 we can't change, so we desperately need a negative 1 on top. Well, same thing as we did before. We can't just subtract 1. We're going to have to add 1 as well. That might seem like a never-ending cycle, but fortunately, we only have to do it for this term. Then we can move the constants over to this other side, to this last term, and the same problem will not appear there, as we'll see. So last but not least, 1 over s plus 1 plus 3 s minus 1 over s minus 1 squared plus 2 squared plus, notice we had 3 outside of this and we had plus 1, so we'll add 3. That'll give us 8 of these terms here. S minus 1 squared plus 2 squared. And the only thing we need to tweak here is we're going to need a 2 on top, and we'll need a half then to compensate for that. This will be the transform of a sine function. Finally, we have our solution. We're going to take the inverse. That'll transform us back to the time domain, and each of these terms can be done one by one. This will be e to the negative t, the 1 over s minus a form. We also have the 3 times the transform of basically a cosine of kt, so 2t, and we have an s minus 1 both times, and that'll give us an e to the t as a multiplier, using this combination of rules here. And similarly, we're going to have a 4 times sine of 2t from the 2 over 2 squared, but we have all the s's shifted, so it gives us another exponential e to the t as well. And that would be our final solution. As always, with that length of computation, it's probably a good idea to check that what we have is correct. In this case, because the derivatives get a little tedious, we will write that out in the solutions, but won't go through all the details in the video.